Now let us see types of singularities. There are four types of singularities: isolated singularities, poles, essential singularities, and removable singularities. First, let us see the definition of isolated singularities. So, isolated singularities means here we know how to find out the singular points. That is the neighborhood of that particular singular point. The function will be analytic. That is, there exists no other singular point in its neighborhood. That is what the definition is given. There is no other singularity in its neighborhood. For example, if we notice this function f of z is equal to z by z minus 1 into z minus 2, here we know that z equal to 1 and z equal to 2 are both are singular points. Okay, suppose if you consider 1, the neighborhood point to this 1 is nothing but the nearby points. The nearer point means it might be 1.01 or 1.5, 1.9 like this. So if we consider those points, at those points the function will be analytic. So which means that in the neighborhood point the function is analytic, so that this is the one and only singular point. Okay, and then similarly z equal to 2 is the singular point. In its neighborhood there is no other singular point, so we can call as the z equal to 1 and z equal to 2 are called as isolated singular points. So this is the example for isolated singularities. Next is poles. Poles means first it should be an isolated singularity, and apart from that the principal part of the Lorentz series expansion has only finite number of terms. Okay, so here if we notice this example 1 by z into 1 minus z whole square, here the singular point is z is equal to 0 is one of the singular point and z equal to 1. So 0 and 1 are the singular point, and it is first of all isolated singular point, and it is also called as poles. Why we are calling it as poles means if you expand this function, it contains a principal part, and in that principal part it contains only finite number of terms. Okay, so how to identify the principal part contains finite number of terms means actually here we have to split it into partial fraction and then applying binomial expansion. That is what we do, usually we will do in Lorentz series expansion, like that we have to do. So after expanding it, if we notice that principal part will contain only finite number of terms, so that these two isolated, that is singular points, are called as poles. So next, coming to removable singular point. Removable singular point is, it should be, the singular point is called a removable singular point if limit f of z should exist and is finite. That is, if you consider this example f of z is equal to sine z by z, here z is equal to 0 is called as removable singular point. Why it is called as removable singular point? If you substitute this value, that is z equal to 0 in the function, sine 0 is equal to 0 divided by 0, so 0 by 0 is an indeterminate form, which means that the function is not defined at that point z equal to 0. But when we take a limit z tends to 0 for this function sin z by z, here first if you directly substitute, it becomes 0 by 0 indeterminate form, so we can apply L'Hospital rule. So if we apply L'Hospital rule, we have to differentiate numerator separately and denominator separately with respect to the variable. So sin z differentiation becomes cos z and z differentiation is 1. Now if we apply the limit z tends to 0, cos 0 is 1 and divided by 1, which is equal to 1 is the answer. So even though the function is not defined at the point z equal to 0, but while taking limit z tends to 0, it exists and it is also finite value we are getting. So that we can say that this z equal to 0 is the removable singular point. Next is essential singular point. Essential singular point is, first of all, it should be an isolated singular point, and the principal part of the Lorentz series should contain infinite number of terms. So already in poles what we noticed is the principal part should contain finite number of terms, whereas for essential singularity the principal part should contain infinite number of terms. Then such a singular point is called as essential singular point. Here again z equal to 0, that is at z equal to 0 only the function is not analytic. So that z is equal to 0 is called as singular point. And why it is called as essential singular point means if you expand it, that is for example expansion of this e power 1 by z is e power 1 by z expansion is what 1 plus z by 1 factorial. So here 1 by z by 1 factorial plus 1 by z whole square by 2 factorial. So it goes on like this. If we notice, principal part of the Lorentz series expansion means the negative part of z is the principal part. So here if you notice each and every term z is z having the negative power. Okay, so and it goes up to infinity. Okay, so that the principal part of the Lorentz series expansion contains infinite number of terms, so that here we can say z equal to 0 is an essential singular point.